Okay, so part 3 of numerical methods with numerical methods for partial differential equations practice final exam. So number 8, for the linear system arising from the one-dimensional Poisson equation AU equals B, where A is a standard tridiagonal second difference matrix. Here A through F respectively. Derive the Jacobian iteration, derive the Gauss-Seidel iteration, derive the SOR iteration, explain the role of relaxation parameter omega, determine qualitatively why SOR can converge much faster than Jacobi, and for F, state the approximate optimal omega for model Poisson problem. So this is just an overview of this one. So this is a Jacobi Gauss-Seidel. SOR is A equals D minus L minus U, where D is the diagonal, and this negative L is the lower triangular part. Negative U is the upper triangular part. For our Jacobi, the D here, U, K plus 1 equals L plus U, U to the K there. So U at iteration K, if you want to call it that, plus B. So the U at iteration K plus 1 equals inverse D, L plus U, U to the iteration K, plus inverse D, B. So the Gauss-Seidel D minus L, U to the iteration K plus 1, capital U, U to the K plus B. And our SRO is D minus omega L, U to the K plus 1, and that equals bracket 1 minus omega D plus omega U, close bracket, lowercase u, iteration K, plus omega B. So the parameter omega controls relaxation. From 0 is less than omega is less than 1, that's under relaxation. And for 1 is less than omega is less than 2, that's over relaxation. For Poisson problems, SOR can converge faster because it damps low frequency error modes better than Jacobi. For the 1D Poisson problem, omega sub OPT, that's approximately 2 over 1 plus sine pi h. And for small h, omega sub OPT is about 2 minus 2 pi h. So that's number 8. Moving along to number 9. Okay, number 9, we consider u sub t equals d u sub xx plus lambda u, where d is greater than 0 and lambda belongs to all real numbers. Use forward Euler and time and center differences in space. Part A, derive the finite difference method. Part B, find the amplification factor. Part C, determine the stability condition involving d, lambda, delta t, and delta x. Part D, discuss how positive reaction lambda greater than 0 changes stability. And Part E, compare with backward Euler. So this is the stability of a reaction diffusion equation. So our equation u sub t equals d u sub xx plus lambda u. Forward Euler plus center differences gives u sub j n plus 1 equals u sub j n plus s. I'm just quantity u sub j plus 1 n minus 2 u sub j n plus u sub j minus 1 n plus delta t lambda u sub j n, where s equals d delta t over delta x squared. So if we insert the Fourier mode, u sub j n equals g to the n e to the I j theta, then g equals 1 plus lambda delta t minus 4s sine squared of theta over 2. Stability requires absolute value of g to be less than or equal to 1 for all theta. So therefore we could say that negative 1 is less than or equal to 1. Negative 1 is less than or equal to 1 plus lambda delta t minus 4s sine squared of theta over 2 is less than or equal to 1. And then from there, 1 plus lambda delta t minus 4s is greater than or equal to negative 1. So 4s minus lambda delta t is less than or equal to 2. From there, the upper bound requires 1 plus lambda delta t is less than or equal to 1, so lambda is less than or equal to 0. If lambda is greater than 0, the continuous equation itself has growing modes. So one usually analyzes stability relative to the expected physical growth rather than requiring absolute value of g be less than or equal to 1. For lambda is less than or equal to 0, a sufficient condition is delta t times this quantity 2d over delta x squared minus lambda over 2 is less than or equal to 1. And our backward Euler is going to give us g equals 1 over the quantity 1 minus delta t, parentheses, lambda minus 4d, delta x to negative 2, sine squared of theta over 2, close parentheses. And it is much more stable for the diffusive part and can handle larger time steps. Okay, so that's number 9, and moving along to number 10. So for number 10, consider the two-dimensional heat equation, u sub t equals kappa, parentheses, u sub double x plus u sub double y. A, B, C, D, E, respectively. A, explain why a fully implicit method produces a large, sparse linear system. Part B, derive a Piesman-Rashford ADI model. Part C, show how each half step reduces to a collection of tridiagonal solves. Part D, discuss stability advantages compared with explicit methods. And Part E, discuss splitting error and expected accuracy. So this is alternating direction implicit method for u sub t equals kappa, parentheses, u sub xx plus u sub yy. A fully implicit method gives us directions. The Piesman-Rashford ADI model is this, parentheses I minus delta t, kappa over 2 Lx, parentheses, close parentheses, u to the n plus 1 over 2. That equals parentheses I plus delta t, kappa over 2 Ly, close parentheses, u to the n. And then parentheses I minus delta t, kappa over 2 Ly, close parentheses, u to the n plus 1, equals parentheses I plus delta t, kappa over 2 Lx, u to the n, u, close parentheses, u to the n plus 1/2. My apologies if I mispronounce any of that. I'm just going through this quickly. So we could say here the first half step solves tridiagonal systems in the x direction. Second solves tridiagonal systems in the y direction. This ADI avoids solving one huge 2D system. It replaces it with many 1D tridiagonal solves. Okay. For heat type problems, ADI is typically unconditionally stable. ADI referring to alternating direction implicit method. So its accuracy is usually second order in time and space, assuming center differences in symmetric splitting. The splitting error arises because the x and y operators are handled separately. Okay, so that was part 3. Thank you very much and have a great day.